What do a glamorous 1940s Hollywood star and a revolutionary new data format have in common? Sounds like the start of a joke, right?
Yeah, it does a bit, but the answer actually gets to something fundamental. Interoperability.
Exactly. We're talking Hedy Lamarr,
Yeah.
an amazing inventor, not just an actress. Her work on frequency hopping spread spectrum, well, it laid groundwork for Wi-Fi, Bluetooth, all sorts of things.
Right. And her genius wasn't just the tech itself, but the principle behind it, getting different systems to communicate reliably without stepping on each other's toes.
It's a perfect example of what economists call a general-purpose technology, or GPT.
Yeah.
Something that doesn't just tweak things, but opens up completely new possibilities.
And that's the perfect lead-in to our topic today, VectorDiff. It's a new data format, but we think it has that same kind of GPT potential. Really transformative.
So our mission today, in this deep dive, is to unpack why VectorDiff might become this universal language for describing change. And believe me, it goes way beyond its origins in, like, vector animation.
Yeah, definitely. We'll look at the core idea, how it actually works under the hood, and then jump into some, frankly, surprising applications, science, industry, even fundamental physics.
Okay, so maybe tease the core concept. What's the big idea?
The magic of VectorDiff, if you want to call it that, is how it describes dynamic stuff, not as, frame after frame after frame like a movie.
Right, not like static snapshots.
Exactly. Instead, it defines an initial state, they call it the base scene, and then it records a really precise, meaningful history of transformations, the timeline.
That's about the changes, the history of how things evolved.
Precisely. It's all about compactly encoding that state change history in a way that retains meaning. Semantically rich is the term often used.
And the payoff is,
Well,
it sounds like it's more than just smaller files, although that's part of it.
Oh, much more, yes. Drastically reduce file sizes because you only store the differences, the deltas, but you also get mathematical precision, infinite scalability because it's vector-based, true interactivity.
And platform independence. It sounds like a different philosophy entirely.
It really is.
Yeah, let's dig into that, this differential philosophy. What's the problem VectorDiff is actually trying to fix?
Well, you could almost call it a crisis of representation for complex, dynamic data, especially multi-dimensional data.
How so?
Think about your standard video file, like an MP4. It's just pixels, right? A grid of colors changing over time. It throws away all the underlying structure, the meaning.
Which means huge files, and you can't really interact with objects inside the video. You can't easily query it.
Exactly. And even if you look at traditional vector animation formats like SVG with semi-hill, they keep the geometry, sure, but they can become incredibly long-winded, very verbose.
Right. Not really designed for, say, tracking thousands of tiny changes happening constantly in a scientific simulation.
Precisely. So VectorDiff's solution is built on that core principle, base scene plus timeline. Store the start state, then just log the changes over time. That's the differential part. Only store the delta.
Okay, let's break that down. The base scene, that's like the initial setup at time zero.
Exactly. It's an array of vector object elements. Each object gets a unique ID, a type like rect, ellipse, path, it's starting geometric data, and it's styling. Your whole scene at T0.
Got it. And the timeline.
That's an object where the keys are timestamps. Really precise timestamps, like 1.05. And the value for each timestamp is an array of transformations happening at that exact moment.
And each transformation says, okay, target object ID in number 123, and move it this much or rotate it that much.
Yep. Translate, rotate, scale, change color, whatever it might be. It targets a specific vector object using its target ID.
Now, there's a technical detail you mentioned that sounds important. All geometric changes stack up on a single transform attribute. The original shape data doesn't change. Why is that significant?
Ah, yes. That gives you predictability and what's called compositional transforms. It means you can layer transformations reliably.
Like rotating an object that's already moving.
Exactly. The math stays clean. You apply the sequence of transforms to that single attribute. The underlying geometry remains pristine. It avoids a lot of potential headaches and precision issues.
Okay, that makes a lot of sense. So for you listening, this isn't just nerding out on file formats. This differential approach translates to real benefits.
Huge benefits. Incredible efficiency, like we said, pinpoint mathematical precision no matter how much you zoom in, and crucially, the ability to actually query and interact with individual elements within the animation over time.
That's semantic richness. You're not just watching pixels. You're interacting with meaningful objects that have a history.
That's the core idea.
All right, let's broaden out. Where is this actually being used? Let's talk applications. This is where it gets really interesting, moving beyond animation. First up, industrial IoT and digital twins.
Yeah, this is a fascinating area. The Industrial Internet of Things, IIoT, often struggles with what people call a digital Tower of Babel.
Too many different ways for machines to talk.
Pretty much. You've got complex standards like OPC UA, which are very detailed but can be heavy and slow. Then you have MQTT, which is super lightweight for messaging.
But it doesn't inherently define what the data means, right? It just passes messages.
Exactly. And digital twins, these virtual copies of real-world machines or systems, they desperately need a standard way to pull all this data together and track the history of an asset accurately in real time.
So VectorDiff comes in as, what, the common language?
Sort of the lingua franca, yeah. It complements something like MQTT. MQTT handles the message delivery. VectorDiff defines the content and meaning. So a machine tool, a robot arm, even a sensor becomes a vector object.
And its timeline becomes its life story.
Precisely. An inviolable semantic chronicle is a phrase I like. It logs every operation, every fault, every maintenance action, every configuration tweak.
And because it's differential, the updates center of the network are tiny.
Ultra-compact differential transformations. It slashes network bandwidth and storage costs compared to sending full-state snapshots all the time.
The impact there feels huge for things like predictive maintenance.
Absolutely. Imagine an AI wanting to understand why a machine is failing. Instead of trying to piece together cryptic logs from different systems,
It just asks for the VectorDiff timeline for RoboDarm 7.
and gets its complete standardized operational history. The AI can literally watch the machine's life, see the sequence of events leading up to the failure. It's not just if it failed, but how and why. That's a game changer for root cause analysis and prediction.
Okay, that's powerful. From factories to the whole planet. Earth system science. Climate modeling. How does VectorDiff fit there?
Climate science has its own data challenges. Traditional formats like NetCDF or DREAB are often grid-based. Storing and accessing this data, especially in the cloud, can be really inefficient.
Like needing hundreds of tiny requests just to get the metadata for a specific region or time.
Exactly. And beyond efficiency, the science itself is shifting, more focus on object-based analysis.
So tracking a hurricane as an object, not just looking at grid cells representing wind speed.
Precisely. Tracking hurricanes, ocean eddies, atmospheric rivers as distinct entities with their own life cycles, and current formats aren't ideal for that. Plus, there's a need for smart compression that doesn't lose vital scientific information, bitwise real information, as they say.
So VectorDiff flips the script. Instead of storing grids and extracting objects later.
You store the objects directly. A hurricane becomes a vector object with a unique ID. Its timeline tracks its entire journey location, shape changes, intensity fluctuations.
Like semantic compression for scientific phenomena.
That's a great way to put it. It inherently keeps the scientifically meaningful information. It's also perfect for things like Lagrangian trajectory analysis, tracking thousands of virtual particles drifting in the ocean or atmosphere. Each particle is an object with a timeline.
Wow. So the impact on research could be massive.
Radically simpler, potentially. Instead of wrestling with 100 terabytes of grid data just to find all the Atlantic cyclones in a given year.
A researcher could just query, give me the timeline for all vector objects of type cyclones in the Atlantic region.
Exactly. It democratizes access to complex data and could seriously accelerate discovery by making it easier to focus on the phenomena themselves.
Okay, let's shift again. Financial markets. High-frequency trading. Seems like a totally different world.
It is in terms of speed. High-frequency trading protocols like ITCH are raw binary streams optimized purely for latency. Nanoseconds matter.
But they lack meaning. They're hard to analyze after the fact.
Very hard. They're not designed for archiving, replaying market events, or doing deep analysis on the history of the order book in a standardized semantic way. That kind of analysis is currently very difficult and expensive.
So VectorDiff isn't trying to replace ITCH for live trading.
No, definitely not. Binary is still king for that raw speed, but VectorDiff becomes the ideal format for archiving and analyzing that data, the perfect canonical format.
So the entire order book for, say, Apple stock could be one vector object.
Conceptually, yes. And its timeline would record every single event, every new order, cancellation, trade with nanosecond precision, who placed it, the volume, the price, the event type, all captured semantically.
And incredibly compactly because it's differential.
Exactly. You're only recording the changes to the order book state.
What could that unlock?
Well, imagine exchanges offering historical market data in VectorDiff format. That creates whole new possibilities for market analysts, researchers, regulators.
And for AI.
Ah, yes. AI could be trained to detect really sophisticated market manipulation tactics, things like spoofing, where
Wow.
traders place fake orders to create false impressions.
Or layering, building up fake walls of orders.
Right. Analyzing the sequence and intent in the timeline could reveal these patterns in a way that's currently almost impossible or computationally requires huge resources. It's about understanding the story of the order book, not just the numbers. Big implications for transparency and security.
That idea of chronicling history, it makes me think about games.
Hmm.
Especially complex simulation games like Dwarf Fortress or EVE Online. They generate these incredibly rich histories, right? Civilizations rise and fall, legendary items get forged.
But that history is often buried, isn't it? It's generated by the simulation, but it's not always easily accessible or structured for the player or even for the game's own AI to reason about.
Yeah, it feels like a missed opportunity sometimes.
Totally. And this is where VectorDiff could be amazing. It could become the chronicle format for these persistent, procedurally generated worlds.
So the goal isn't just the final state of the world, the map at the end.
No. The goal is a single VectorDiff file that contains the entire history. Every significant entity, a civilization, a specific character, a unique artifact, is a vector object.
With its own timeline, recording its birth, its actions, its demise, its interactions.
Exactly. A complete, potentially nonlinear history. The game itself then becomes an interactive player of that history and a continuator of it. The world genuinely remembers itself.
Wow. That opens up entirely new kinds of gameplay, doesn't it?
Oh, absolutely. Imagine being able to rewind history in the game world. Trace the lineage of a sword back through centuries of owners. Analyze a pivotal battle from any angle at any moment in time.
It's like version control for narratives, a Git for virtual histories.
That's a fantastic analogy, a Git for narratives. Modders could literally fork the history at a certain point, create an alternate timeline, maybe even merge changes back in. It changes the player's relationship with the game world from just experiencing it to potentially curating or exploring its entire past.
Okay, we've gone from machines to planets to markets to virtual worlds. Let's get even more fundamental. What about understanding the brain? Neuromorphic computing.
Right. Neuromorphic computing is really exciting. It's inspired by how the brain works, using spiking neural networks, or SNNs. They process information based on discrete events or spikes rather than continuous calculations.
And the promise is huge energy efficiency compared to traditional AI.
Exactly. But development is tricky. One big hurdle is the lack of standard tools and formats. Every research group, every simulator seems to use its own proprietary binary format for recording and analyzing SNN activity. It creates silos.
Sounds like a classic interoperability problem. And VectorDiff's philosophy seems like a natural fit. Objects changing state over time.
It's a perfect fit. Each neuron in your simulated SNN could be a vector object.
And its timeline that just records the spikes.
Precisely. A time-stamped log of every single spike that neuron generates. The entire network's activity, all its dynamics, captured coherently in one semantic file or a collection of linked files.
So VectorDiff could become the standard data format for neuromorphic simulations.
That's the vision, like the PDB format did for structural biology, providing a common language. It would break down the silos, enable shared tools for visualization, debugging, analysis. It could really accelerate the whole field of brain-inspired AI.
Okay, one last application area, and this one feels maybe the most profound. Epigenetics and the information theory of aging.
Yeah, this connects to David Sinclair's work. His information theory of aging proposes that aging isn't mainly about mutations in our DNA sequence itself.
But more about the loss of epigenetic information,
Right.
the instructions that tell genes when to turn on or off.
Exactly, like a CD getting scratched over time. The music, DNA, is still there, but the player, cellular machinery, can't read it properly because the surface information, epigenome, is degraded.
And the theory suggests this loss of information might be reversible, but we need better ways to track it.
Right. We lack a formal computational model to really capture how this complex epigenetic landscape changes dynamically over a lifetime.
Enter VectorDiff.
Potentially, yes. It offers a formal language for modeling this. A cell, or maybe even the entire epigenome, becomes a vector object.
The base scene would be the young, ideal epigenetic state.
Exactly, the pristine information state. And the timeline would meticulously record the sequence of epigenetic changes, epimutations that accumulate over time, recorded as compact semantic transformations.
So it becomes a computational framework to actually test the information theory of aging.
That's the really compelling part. You can build computational models based on the theory and represent their evolution using VectorDiff. And theoretically, if the theory holds, that VectorDiff file describing a cell's aging history contains the blueprint for its decline.
Which means reversing the timeline.
Could computationally point towards pathways for rejuvenation. It turns a biological theory into something you can potentially model, test, and maybe even manipulate computationally, guiding directions for regenerative medicine. It's speculative, but very powerful.
Wow. Okay, we've covered some incredible ground, from very practical applications to these really deep fundamental ideas. Let's pivot slightly. Can we really think of VectorDiff as like the language of change itself, connecting to really basic concepts in physics and information theory?
This is where it gets beautifully abstract, but I think the connections are real. Let's start with Kolmogorov complexity.
Okay, remind us. That's the ultimate measure of compression, right? The
Yep.
shortest possible description of something.
Essentially, yes. It's the length of the shortest computer program that can generate an object or piece of data. It's the absolute measure of its true information content. Most compression algorithms we use, like zip, they don't really get close because they don't understand the structure or the generative process behind the data.
But VectorDiff, with its base scene plus timeline, that is a program in a sense, a recipe for generating the history.
Exactly. It is a program that step by step generates the object's entire state history. And because it's differential, only storing changes, its program length is inherently minimized, especially for systems where changes are incremental or follow rules.
So it naturally tries to find a compact description of the evolution.
It strives to describe the system's trajectory as compactly as possible, getting closer to that theoretical Kolmogorov complexity limit. This makes it incredibly powerful for systems that might look complex on the surface.
But whose underlying rules of change are relatively simple.
Precisely. Systems with high state complexity but low evolutionary Kolmogorov complexity. Think physical simulations, biological growth patterns, maybe even aspects of financial markets. VectorDiff is optimized for describing how things become, not just what they are.
That's a profound link. What about physics itself, the principle of least action?
Another deep one. This principle is fundamental in physics. It basically says that the actual path a physical system takes between 2 points in time is the one that minimizes, or makes stationary, a quantity called action. It describes the entire trajectory holistically.
Not just moment-to-moment forces, but the overall path.
Right. And VectorDiff gives us a computational way to represent this. A vector object could represent a physical system. Its base scene defines its initial conditions, position, and momentum.
And its timeline becomes its path through space-time, its world line.
A discrete computational representation of its world line, yes. The timeline essentially encodes the trajectory.
So the principle of least action could almost be used to validate a timeline, to check if it represents a physically plausible path.
You could think of it that way. It starts to blur the line between just storing data and actually embodying the physical model. A VectorDiff file isn't just a recording of a simulation.
It's almost like the simulation itself at rest.
That's a great way to capture it. This enables a whole new level of interoperability for simulations. Different simulation engines could potentially read and write VectorDiff files that represent physically valid histories according to fundamental principles. It's another one of those Hedy Lamarr moments, creating a new abstraction layer.
Okay, let's take the final, most speculative leap. Digital physics, the it-from-bit idea. Could the universe itself operate like this?
Right. This is definitely out there, but intellectually stimulating. Digital physics thinkers like Konrad Zuse, Stephen Wolfram, Max Tegmark, they propose that maybe the universe, at its most fundamental level, is computation, like a giant cellular automaton.
In John Archibald Wheeler's It from Bit, the idea that physical reality emerges from information processing bit.
If these ideas hold any water, then the universe's evolution must be a sequence of discrete state changes governed by computational rules, which are the laws of physics.
And VectorDiff provides a formal structure that looks surprisingly like that.
It offers a concrete data structure that seems isomorphic to that concept. In this view, the universe's state at any instant is an unbelievably complex vector object, the base scene, maybe the state right after the Big Bang.
And the timeline is the entire history of everything, every interaction, governed by physical laws.
Exactly. It becomes a potential model, a language, for how a universe computer might actually store and process its own history. If physics boils down to information, and change boils down to computation.
And a universal, efficient semantic format for describing change history isn't just useful, it's potentially fundamental.
It positions VectorDiff, perhaps aspirationally, as a contribution not just to technology, but maybe even to how we model and understand reality itself. A legacy like Lamarr's, rooted in enabling fundamental interoperability, but this time for change itself.
Mind-bending stuff. Okay, so given all this potential, from the practical to the deeply theoretical, how do we actually get there? What needs to happen for VectorDiff to fulfill this vision? We need some strategy.
Absolutely, it won't happen automatically. The first and probably most critical step is aggressive and open standardization.
Learn from history, right?
Yeah.
PDF, HTML, GLTF. Their power comes from being open standards.
Totally. VectorDiff needs that same path. The immediate move should be to establish something like a W3C community group. It's a relatively low barrier to entry, invites broad participation, builds community quickly, and it's perfect for incubating the idea and getting out a version 1.0 specification.
And then longer term.
Aim for formal working group status, maybe within the W3C, or perhaps a group like the Kronos group. They handle standards like OpenGL, Vulkan, and importantly, GLTF, so they have experience with graphical standards and managing the associated IP frameworks.
Eventually, maybe even an ISO standard like GLTF 2.0 achieved.
That would be the ultimate goal for broad global adoption and long-term stability.
Okay, standardization is key.
What else? Ecosystem building. Critically important. VectorDiff's value grows exponentially with the number of tools and libraries that support it. The focus cannot be on closed proprietary applications.
It needs to be easy for developers everywhere to use it.
Exactly. That means prioritizing core libraries, maybe under a name like @VectorDiff Core, that are lightweight, minimal dependencies, easy to integrate, and available in the key languages developers use. TypeScript, JavaScript for the web, Python for data science and scripting, C++ and Rust for high-performance applications.
Make it almost frictionless to adopt.
Yes, and then actively build plugins for the major existing platforms. Scientific visualization tools like ParaView, 3D Slicer, game engines Unity, Unreal, data analysis environments like Jupyter Notebooks, IIoT platforms. Native import and export in these tools is crucial.
Again, learning from GLTF, its ubiquity in tools, was a major driver of its success.
Absolutely. Make it the default, easy choice for dynamic vector data.
And the final piece, how it's presented to the world.
Visionary positioning. The strategic communication right from the start has to emphasize this fundamental cross-disciplinary potential. It cannot be pigeonholed as just a better format for vector animation.
It needs to be framed as this universal language of change we've been talking about.
Yes. Actively promote the vision. Highlight the diverse applications. Digital twins, climate science, finance, neuromorphics, even the physics connections. Tell that bigger story.
Why is that so important?
Because that's what will attract the innovators, the researchers, the startups from completely different fields to start experimenting with it in ways the original creators might never have imagined.
Those unforeseen applications, like happened with Hedy Lamarr's frequency hopping, its biggest impacts were far beyond its initial military intention.
Precisely. Those unexpected uses are what ultimately prove its GPT status and define its true revolutionary legacy. You need to inspire people to think big with it.
So to wrap this up for everyone listening, we've really gone deep on VectorDiff today, and I think it's clear this is way more than just another file format.
It really represents a new principle, doesn't it? A universal way to record the history of dynamic systems interoperably.
Its power to encode change efficiently, precisely, and with meaning seems genuinely revolutionary across so many fields. Industry, science.
And potentially even helping us grapple with fundamental theories about information, physics, and reality itself.
Connecting this all together, it paints a picture of a future where maybe every process, every changing system, from a cell aging to the cosmos evolving,
could potentially be understood, analyzed, maybe even simulated or manipulated using this unified language of change.
So the final thought for you is, what happens when we have a get for reality? What new discoveries are unlocked? What unexpected connections emerge when change itself starts speaking a universal tongue?
It's a powerful question. It suggests a future where our understanding of the dynamic world becomes much deeper, much more integrated.
Something to definitely keep an eye on.